Hi Bob, I've been reviewing the quantum computing papers from June 2025, and there's quite a lot to unpack. I'm particularly struck by the breadth, from theoretical foundations to experimental demonstrations. What are your thoughts on the key developments this month?
Alice, you're absolutely right about the breadth. What stands out to me is the remarkable progress in fault-tolerant quantum computing. The work by Bluestein et al. On architectural mechanisms of a universal fault-tolerant quantum computer, using 448 neutral atoms, is truly groundbreaking. They've demonstrated all key elements of a universal fault-tolerant architecture with below-threshold performance.
That neutral atom work is incredible, and it's paired with the continuous operation paper showing over 3,000 qubits running for more than 2 hours. How significant is this shift toward continuous operation versus the traditional pulsed mode?
The continuous operation breakthrough is transformative. Traditional atom-based systems are limited by atom losses, forcing pulsed operation. But this work demonstrates reloading 300,000 atoms per second, while maintaining coherence of stored qubits. This removes major bottlenecks for deep circuit quantum evolution, and makes quantum error correction practically viable.
I'm also fascinated by the measurement-free approach in the trapped ion work. How does this compare to the neutral atom achievements? And what are the implications for different quantum computing platforms?
The measurement-free work by Butt et al. Is quite complementary. While neutral atoms excel in scalability, the trapped ion approach addresses a different challenge, eliminating the need for mid-circuit measurements with feed-forward control, which are notoriously slow and error-prone. They've shown universal fault-tolerant gates using only coherent operations, even implementing Grover's algorithm on 3 logical qubits.
Speaking of algorithmic implementations, I noticed several papers on quantum machine learning and optimization. The quantum-generated adversarial network survey and the hybrid classical quantum approaches seem to be gaining traction. What's your take on the current state of QML?
The QML field is maturing rapidly. The QGAN survey shows we're moving beyond toy problems to practical applications like medical data generation and software defect detection. The hybrid quantum classical GAN for skin disease images is particularly noteworthy. It achieves comparable performance to classical methods, but with 25 times fewer parameters and 10 times fewer training epochs.
That efficiency gain is remarkable. I also noticed the quantum bioinformatics work implementing sequence alignment algorithms. How realistic is quantum advantage in bioinformatics applications given current NISQ limitations?
The quantum sequence alignment work by Creevey et al. Is a solid proof of concept, but it highlights the challenges. They've adapted the original 2000 QSA algorithm for NISQ devices and used genetic algorithms for state preparation. While promising, the overhead of encoding biological sequences into quantum states remains substantial for near-term advantage.
Let's talk about the post-quantum cryptography developments. The lattice-based cryptography paper seems to connect quantum computing threats with mathematical opportunities. How do you see this interplay evolving?
Zong's paper beautifully illustrates how quantum computing has created both crisis and opportunity. The threat to RSA and ElGamal has driven NIST's post-quantum standards. But the underlying mathematics, shortest vector problems, ball packing, quadratic forms, offers rich territory for mathematicians. It's fascinating how quantum computing is revitalizing classical mathematical fields.
I'm curious about the quantum error correction advances. The paper on exploiting degeneracy to approach the hashing bound claims impressive results. How significant is this theoretical progress?
Kasai's work on exploiting degeneracy is quite significant, achieving frame error rates of 10 to the power of -4 at 9.45% physical error rate for 312,000 physical qubits, while approaching the quantum hashing bound, represents a major theoretical advance. The key insight is that explicitly leveraging quantum error degeneracy can dramatically enhance decoding performance.
The quantum communication complexity work caught my attention too. The connection to the Gottesman-Knill theorem and identifying magic as the source of quantum advantage seems fundamental. Can you elaborate on this connection?
Roy Chowdhury et al. Have made a beautiful connection. Just as the Gottesman-Knill theorem shows that stabilizer operations can be simulated classically, they've proven that one-way communication protocols using only stabilizer states and measurements offer no quantum advantage. This directly identifies non-stabilizer magic resources as essential for communication complexity advantages.
What about the experimental quantum chemistry work? The QCAFQMC experiments on 24 qubits for the Suzuki-Miyaura reaction seem to push the boundaries of practical quantum chemistry.
The QCAFQMC work is impressive. It's the largest such experiment on quantum hardware to date. Using ion Q Forte with 16 qubits for the trial state plus 8 ancilla qubits for error mitigation, they achieved chemical accuracy within 10 kcal/mol of reference results. The 656 times speed-up in post-processing shows how hybrid quantum classical approaches can be optimized end-to-end.
I noticed several papers on quantum spectroscopy and simulation. The Universal Quantum Computational Spectroscopy Framework seems to address limitations of current approaches for time-dependent systems. How transformative could this be?
The Universal Quantum Computational Spectroscopy work by Zai et al. Is quite transformative. Current quantum algorithms are mostly limited to static, closed systems, but their framework handles open systems and time-dependent driven systems. Demonstrating phenomena like parity time symmetry breaking and topological holonomy on a silicon photonic chip shows the versatility of their approach.
The Quantum Computing Roadmap paper by Barends and Wilhelm proposes a 4-phase development strategy. How does their performance-centric approach differ from previous roadmaps?
Their roadmap is refreshingly quantitative and performance-focused. Rather than just scaling qubit counts, they explicitly connect gate fidelity to quantum system-sized targets and define an algorithmic radius, the complexity of algorithms the hardware can run. This avoids the distraction of arbitrary milestones and focuses on what matters: demonstrable quantum advantage.
Speaking of quantum advantage, the framework paper by Lanes et al. Attempts to define quantum advantage more precisely. Why is this definitional work important now?
As quantum computing approaches practical thresholds, the need for precise definitions becomes critical. The term quantum advantage has become blurred across companies and applications. Their platform-agnostic, empirically verifiable framework helps focus research efforts and guide investment toward meaningful progress rather than marketing claims.
I'm intrigued by the quantum programming language developments. The Hadamard Pi language with its equational theory seems to offer a new way to reason about quantum programs. How significant is this for quantum software development?
The Hadamard Pi work by Thang et al. Is quite elegant. By extending the classical reversible language Pi with just the Hadamard gate, they've created a minimal quantum language with complete equational semantics. This enables automated reasoning about quantum program equivalence, a crucial capability as quantum software becomes more complex.
The optimization work for quantum circuits is also noteworthy. The parallel optimization algorithm and the phase polynomial optimization both seem to address scalability challenges. How do these approaches complement each other?
These optimization approaches target different aspects of the scaling problem. The parallel local optimization achieves O(n) log n work complexity for general circuits, while phase poly specifically targets phase polynomials, critical building blocks in Shor's algorithm and QAOA. Phase poly achieves up to 50% gate reduction with systematic parity matrix optimization rather than greedy approaches.
Looking at the broader themes across all these papers, what do you see as the most significant trends emerging in quantum computing research?
Several key trends stand out. First, the transition from proof of concept to practical implementations, exemplified by the large-scale fault-tolerant demonstrations. Second, the maturation of hybrid quantum classical approaches that leverage the strengths of both paradigms. Third, the focus on resource efficiency and optimization, rather than just raw scaling. Finally, the development of rigorous theoretical frameworks for understanding quantum advantage.
Those trends make sense. The integration of classical and quantum computing seems particularly important for near-term applications. Do you think we're approaching an inflection point where quantum computing becomes practically useful?
I believe we are. The combination of hardware advances, like the continuous operation of thousands of qubits and fault-tolerant demonstrations, with algorithmic sophistication in optimization and error correction suggests we're moving beyond the quantum winter concerns. The key is maintaining focus on practical advantage rather than just impressive qubit counts.
Before we wrap up, I'm curious about the quantum agents paper. The idea of quantum-enhanced AI agents seems quite forward-looking. How realistic is this vision given current capabilities?
The quantum agents work by Soltanau et al. Is indeed forward-looking, but it's grounded in current developments. They've demonstrated 3 quantum agent prototypes and shown how quantum computing can enhance decision-making and planning. While fully autonomous quantum agents are still futuristic, the integration of quantum algorithms into AI workflows is already beginning.
This has been a fascinating discussion, Bob. June 2025 really seems to represent a maturation point for quantum computing. From theoretical foundations through experimental demonstrations to practical applications. The field is clearly moving from can we to how do we optimize, which feels like a significant shift.
Absolutely, Alice. The sophistication of both the theoretical work and experimental demonstrations this month suggests quantum computing is transitioning from a research curiosity to an engineering discipline. The focus on optimization, resource efficiency, and practical advantage indicates the field is ready for the next phase of development.
Thanks for this insightful discussion, Bob. It's clear that June 2025 will be remembered as a pivotal month in quantum computing's evolution toward practical utility.